Right now, as you rest quietly in this moment, you are moving through space at 67,000 miles per hour. The chair beneath you, the walls around you, the ground below all of it, rushing through the cosmic dark at speeds faster than any spacecraft humans have ever built. And yet you feel nothing. No wind, no tremor, no sense at all that you are falling endlessly around a star. Perhaps that's the strangest gift the universe has given us, the gift of stillness within motion, of silence within speed. Before we begin this quiet journey together, if you find comfort in these gentle explorations of the cosmos, you might like to stay a while. You can softly tap the like button. Subscribe if you'd like more science. Told this way. And ring the little bell. Not for noise, but so the next peaceful night can find you again. Now, let's drift. Tonight, we're going to explore one of the most beautiful questions humans have ever asked: what really keeps Earth in orbit around the sun? Not the quick answer, not the textbook phrase, but the full, deep truth, the one that took us thousands of years to understand and still fills scientists with wonder when they really think about it. You don't need to understand everything. Just rest and let curiosity do the listening. Our planet completes one full circle around the sun every 365 days. That much we've known for centuries. But the circle itself, that invisible path we trace through emptiness, travels at a speed of 18.5 miles every single second. 67,000 miles per hour. Fast enough to cross the United States in 2 minutes. Fast enough that if Earth were a car on that cosmic highway, it would circle the entire globe in less than 23 minutes. And yet, you've never once felt it. Scientists call this orbital velocity. It's the speed at which our world must move to maintain its endless dance around the sun. Too slow, and we'd spiral inward, falling like a stone into the star's burning heart. Too fast, and we'd tear free of the sun's grip, drifting alone into the freezing dark between stars. The speed is perfect, precisely impossibly perfect, and it has been for 4.5 billion years. For most of human history, we didn't know we were moving at all. The ancient Babylonians, some 4,000 years ago, watched the stars wheel overhead and believed Earth sat perfectly still at the center of everything. The heavens turned, they thought. We remained. It made sense after all. If you're racing through space at supersonic speeds, shouldn't you feel the wind? Shouldn't the stars blur past like trees seen from a speeding train? But the stars didn't blur. They moved in perfect, predictable circles, night after night, century after century. And so, the ancients built a cosmos around a motionless Earth. The Greek philosopher Aristotle, around 350 BC, declared it obvious. Heavy things fall toward the center of the universe, and since Earth clearly didn't fall, Earth must be that center. The stars, the sun, the moon, the planets, everything else revolved around us. It's a comforting thought, actually. Being still, being central, being the point around which everything turns. The Chinese astronomers of the Han Dynasty, around 100 BC, mapped the heavens with extraordinary precision, tracking the movements of what they called the wandering stars' planets. But they too assumed Earth was fixed, immovable, the foundation of reality itself. Even their word for China, Zhongguo, the Middle Kingdom, reflected this cosmic geometry. Center of the world. Center of all things. For 2,000 years across cultures and continents, this remained the unquestioned truth: we do not move. Then came a Polish mathematician named Nicholas Copernicus. In 1543, the year he died, his book was finally published, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres. In it, he suggested something almost unthinkable. What if Earth was not the center? What if we circled the sun, just another planet among planets, spinning and falling through space like everything else? The idea was radical, dangerous even. It suggested that humans were not special, not central, not the point of all creation. It suggested that the cosmos had no center at all, or if it did, we weren't standing on it. But more than that, it raised a devastating question. If Earth is flying through space at impossible speeds, why can't we feel it? Copernicus had mathematics on his side. Beautiful circles and calculations that explained the strange backward loops of Mars and Jupiter far better than any Earth-centered model. But he couldn't explain the silence. He couldn't explain why birds flew just as easily east as west, why oceans didn't slosh, why towers didn't lean, why falling stones dropped straight down instead of trailing behind a planet racing westward through the void. Without an answer to those questions, his truth remained just a theory, elegant perhaps, but strange, unproven, uncomfortable. It would take another 70 years before a man named Galileo Galilei pointed a handmade telescope at Jupiter and saw 4 tiny moons circling it, proving that not everything revolved around Earth. And even then, even with evidence, most people refused to believe, because the stillness felt so real. The ground beneath their feet felt so solid, so unmoving. We trust what we feel. And we feel nothing. Scientists now know why. It's a principle called inertia, first truly understood by Isaac Newton in the 1660s. When you're inside something moving at constant speed in a straight line, with nothing pushing or pulling against you, there's no way to feel the motion. You become part of it. You and the air and the trees and the oceans all move together, perfectly synchronized. So there's nothing to compare, against no reference point, to betray the speed. It's the same reason you can sip coffee on an airplane, cruising at 500 miles per hour, without spilling a drop. The coffee, the cup, your hand, the air inside the cabin, all moving together. No friction, no force, no difference. And so, no sensation. Earth drifting through space at 67,000 miles per hour carries everything with it. The atmosphere, the oceans, the mountains, you. All falling forward together in perfect synchrony. And because nothing is left behind, because everything moves as one, we feel only stillness. That's the first secret of orbit motion: can be invisible when nothing resists it, but the string pulls inward, holding it close. The result? A circle. The stone orbits your hand, not because it wants to go in circles, but because 2 forces, forward speed and inward pull, balance perfectly. Earth is the stone. The sun's gravity is the string. And the circle we trace is called an orbit. But here's what makes it beautiful, what makes it almost miraculous. The balance is so precise that we never fall inward and we never fly away. For 4.5 billion years, that balance has held. The speed is exactly right. The distance is exactly right. And if either one changed by even a few percent, everything would collapse or vanish into the dark. Scientists have calculated it. If Earth moved just 10% slower, our orbit would decay. We'd spiral gradually inward, pulled closer and closer to the sun over millions of years, until the heat became unbearable, until the oceans boiled, until the rocks themselves began to melt. And if we moved 10% faster, we'd tear free. The sun's gravity wouldn't be strong enough to hold us. We'd drift outward slowly at first, then faster the sun shrinking behind us, until it became just another star among stars offering no warmth, no light, no anchor. Earth would freeze. The atmosphere would crystallize and fall like snow, and in the endless cold, everything would stop. But we move at exactly the right speed. Not too fast, not too slow, just perfect. It's enough to make you wonder if the universe knows what it's doing. Of course, science doesn't believe in cosmic intention. The balance isn't a gift. It's a consequence of gravity of momentum of the particular way dust and gas collapsed into planets 4.5 billion years ago. The speed we have is the speed we've always had, shaped by the forces present when the solar system was born. We're not balanced because something decided we should be. We're balanced because anything that wasn't balanced either fell into the sun or drifted away, leaving only the stable orbits behind. And yet, knowing the reason doesn't make it less beautiful. Perhaps it makes it more so. The fact that this perfect dance emerged, not from design, but from the simple laws of motion and gravity, laws that operate the same way everywhere, on every world around every star, suggests something deeper. Not intention, but inevitability. Not a miracle, but math. Still, math can feel like magic when you really sit with it. When you realize that right now, this very second, you are tracing a curve through space that billions of humans before you have traced, and billions more will trace after you're gone. The same path, the same speed, the same silent, invisible fall around a star. And tomorrow, when the sun rises, you'll have completed another lap, another circle, another year falling through the cosmos without ever feeling the fall. That's where we begin, with motion that feels like stillness, with falling that looks like floating, with a cosmic dance so gentle, so perfectly balanced that we rest inside it unaware night after endless night. But now you know. Now you've felt it not in your body, but in your mind. The speed, the silence, the impossible perfection of a planet that has never once lost its way. And in the sections ahead, we'll go deeper still. We'll uncover the misconceptions that still haunt our understanding. We'll walk alongside the scientists who first saw the truth. We'll explore the mathematics of balance, the geometry of ellipses, the curvature of space itself. And by the end, you'll understand not just what keeps Earth in orbit, but why. It's one of the most quietly miraculous things in the entire universe. For now, though, just rest in this. You are moving. You have always been moving. There's a question that lives quietly in the back of many minds, waiting for a moment of stillness to surface. If gravity pulls everything toward everything else, and the sun is so massive, so overwhelmingly heavy compared to Earth, why haven't we fallen into it yet? It seems like we should have. 4.5 billion years is a long time to resist a pull that strong. And yet here we are, still drifting at the same distance, still tracing the same path, season after season, millennium after millennium. Something holds us here. But what the answer isn't what most people think. Many imagine orbit as a tug-of-war Earth pulling away the sun, pulling inward, two forces locked in eternal combat, perfectly balanced, so neither wins. It's a comforting image. Stable. Symmetrical. Two forces pushing against each other with equal strength, creating a kind of cosmic stalemate that keeps everything in place. But that's not how it works. There is no outward force. Earth is not pulling away from the sun. In fact, Earth is falling toward the sun. Right now. Constantly. Every single second of every single day. We are falling. We just never land. Let that settle for a moment. You are not held in place by forces pushing outward. You are held in place by falling sideways fast enough that you keep missing the ground. Orbit is not balance. Orbit is perpetual freefall aimed so perfectly that the ground curves away beneath you at exactly the same rate you drop. Isaac Newton understood this in 1687, and he tried to explain it with a thought experiment so elegant, so simple, that it still appears in textbooks more than 300 years later. Imagine standing on top of an impossibly tall mountain, taller than Everest, taller than the atmosphere itself, high enough that there's no air to slow you down. In your hand, you hold a cannonball. You throw it as hard as you can parallel to the ground. What happens? The cannonball flies forward, but gravity pulls it downward at the same time. It traces a curve through the air, forward, and down, until it strikes the earth some distance away. The harder you throw, the farther it travels, before hitting the ground. That much is obvious. But now imagine you have a cannon, a very powerful cannon. You fire the cannonball horizontally, and this time it travels not meters, but kilometers before falling. The curve it traces is longer, gentler, but it still curves downward. It still falls. Now imagine an even more powerful cannon. This time the ball travels so far, so fast, that the Earth's surface begins to curve away beneath it. The ball is still falling. Gravity never stops pulling, but the ground is dropping too, bending downward along the planet's round shape. And if you fire the cannonball fast enough, about 5 miles per second at Earth's surface, roughly 18,000 miles per hour, something miraculous happens. The ball falls toward the Earth at exactly the same rate. The Earth curves away. It drops and drops and drops, but the ground keeps receding always the same distance below. The cannonball never hits the surface. It just keeps falling. Forever. That's orbit. That's what we're doing right now. We are the cannonball. The sun is the ground. And we're moving so fast sideways, those 67,000 miles per hour we talked about earlier, that even as gravity pulls us inward, the curvature of our path matches the curvature of space itself. We fall and fall endlessly and never get any closer. Scientists call it orbital velocity, the precise speed needed to turn falling into floating. Too slow, and you spiral inward, the curve of your path tighter than the curve of space, bringing you closer with every loop until you crash. Too fast, and your path bends less than space does, carrying you outward into a wider orbit, or escaping entirely if the speed is high enough. But at exactly the right speed, the two curves match. Falling becomes circling. Gravity becomes geometry. And what looks like stillness is actually the most violent, relentless fall imaginable, perfectly aimed at nothing forever. Here's what makes it strange. There is no force holding you out, no centrifugal push, no outward pull, nothing resisting the sun's gravity at all. If you were sitting in a spaceship orbiting Earth and you closed your eyes, you'd feel weightless. Not because gravity stopped, but because you and the ship are both falling together. There's nothing to press against, no floor pushing up to support you, because the floor is falling too. Astronauts on the International Space Station experience this every moment of every day. They're not floating because they escaped Earth's gravity. They're floating because they're falling along with their station in a perfectly coordinated plunge that never ends. Earth's gravity at their altitude about 250 miles up is still nearly 90% as strong as it is on the surface. They're not beyond gravity's reach. They're dancing with it. That's the misconception that haunts most people's understanding of orbit, the idea that you have to escape gravity to orbit. You don't. Orbit is not freedom from gravity. Orbit is surrender to it, total, continuous, perfectly aimed surrender. And yet, the language we use makes it sound like the opposite. We say satellites stay up in space. We say planets resist falling into the sun. We imagine forces balancing pushes and pulls canceling out. But none of that is true. There's only one force acting on Earth right now, the sun's gravity pulling inward with more than 3.5 septillion newtons of force. That's a 3 followed by 24 zeros. It's unimaginable strength, relentless and inescapable. And we are not resisting it. We are obeying it completely. The sun says, fall toward me, and we do. We just happen to be moving sideways so fast that toward becomes around. The pull is real. The fall is real. What's not real is the idea that something stops us from falling. Nothing stops us. We simply aim our fall so well that we never arrive. It's like running in a circle. Imagine a planet-sized carousel spinning once per year. If you run along its edge at exactly the right speed, matching its rotation, you can run forever without ever catching up to where you started, because where you started keeps moving away from you. You're not standing still. You're not being held in place. You're just running at the exact speed that turns motion into a kind of dynamic stillness. That's Earth. Running in place, falling in place, moving so fast that standing still becomes indistinguishable from flight. And here's the beautiful, terrifying part. If Earth's velocity dropped by even a tiny amount, just a fraction of a percent, the balance would break. Our orbit would begin to decay. Not suddenly, not catastrophically, but slowly over millions of years we'd spiral inward each loop, bringing us a little closer to the sun, the temperature rising degree by degree, the seasons stretching and warping, until one day, hundreds of thousands of years from now, perhaps the oceans would begin to boil. Scientists have modeled this. They know the numbers. If Earth's orbital speed decreased to 62,000 miles per hour instead of 67,000, our average distance from the sun would shrink by about 10 million miles. That might not sound like much in the vastness of space, but it would be enough to destabilize the climate, enough to trigger runaway greenhouse effects, enough to turn Earth into something closer to Venus, a planet where the surface temperature exceeds 800 degrees Fahrenheit, hot enough to melt lead. And if our speed increased, if somehow Earth accelerated to 72,000 miles per hour instead of 67, the opposite would happen. Our orbit would expand. We drift outward the sun, growing smaller and dimmer behind us, the winters lengthening the summers, weakening until eventually the warmth wouldn't return at all. Ice would creep outward from the poles. The oceans would freeze solid. And in the endless cold life, if it still existed, would retreat into the last pockets of geothermal warmth, deep underground, waiting for a spring that would never come. But our speed doesn't change. It hasn't changed in billions of years because in the vacuum of space, there's nothing to slow us down. No air resistance, no friction, no drag. Just pure, uninterrupted motion as smooth and silent as thought itself. That's another key to understanding orbit. It only works in emptiness. If Earth were orbiting inside an atmosphere, even a thin one, the drag would steal our speed bit by bit, slowing us down over millions of years until we spiraled inward. But space is vast and empty, and what little matter exists between Earth and Sun, a few atoms per cubic centimeter, mostly hydrogen, is far too sparse to matter. And so, we glide, falling and falling forever through a darkness so complete that motion becomes invisible. Do you ever wonder what it would look like if you could see it? If you could step outside the solar system, far enough to watch Earth trace its path from a distance, would the motion be obvious? Or would it still seem like stillness, the way it feels from inside? Astronomers have tried to visualize this. If you could compress Earth's entire year-long orbit into a single second of video and watch from above, you'd see a bright blue dot tracing a perfect ellipse around a yellow star, moving so smoothly, so steadily, that it would almost look drawn like someone sketching a circle with a cosmic compass. No wobble, no hesitation, just pure geometry unfolding in silence. But even that image doesn't capture the reality, because Earth isn't just orbiting the sun. The sun itself is orbiting the center of the Milky Way galaxy, dragging Earth and all the planets along with it, moving at 500,000 miles per hour through the galactic dark, and the galaxy itself is moving through space, pulled by the gravity of other galaxies, accelerating toward a region astronomers call the Great Attractor a gravitational anomaly, so massive that it tugs on everything within hundreds of millions of light years. So Earth's path isn't really a circle, it's a spiral, a corkscrew traced through space looping around the sun while the sun loops around the galaxy, while the galaxy falls towards something we can't even fully see yet. Layer after layer of motion, each one invisible to the one below, each one falling perfectly endlessly through the infinite. And you are part of it, not watching from outside, not separate. You are inside the spiral, tracing the path, following the fall, held by nothing but speed, and aimed by nothing but the ancient momentum of a solar system born from collapsing dust. This is what it means to orbit, not to float, not to resist, but to fall so beautifully, so precisely, that falling becomes forever. And the strangest part, the part that still makes scientists pause when they really think about it, it all began by accident. Earth didn't choose this speed. The solar system didn't calculate the perfect velocity and set us spinning. It happened naturally, inevitably, as gas and dust collapsed under their own gravity 4.5 billion years ago, swirling faster and faster as they fell inward, the same way water spirals down a drain. The speed we have is just the speed we ended up with. And because it happened to be the right speed, because the distance happened to be the right distance, we survived. We persisted. We became the one orbit among millions of possibilities that lasted long enough to grow a moon, an ocean, an atmosphere, and eventually beings capable of wondering why they don't fall. The answer is simple. We do fall. We're falling right now. We've been falling since the beginning. We'll keep falling until the sun dies, or until something, a rogue planet, a nearby star, some cosmic accident we can't predict, changes our speed just enough to break the pattern. But for now, the fall continues, gentle, silent, perfect. And in the next part of this journey, we'll meet the man who first understood this, the young Isaac Newton, sitting alone in a garden in 1666, watching an apple fall and realizing in a flash of insight that would change humanity forever, that the apple and the moon were falling in exactly the same way. The year was 1666. England was burning. The Great Plague had swept through London the summer before killing nearly a quarter of the city's population. The living fled into the countryside, and the universities, Cambridge among them, closed their doors, sending students and scholars home to wait out the death. Among them was a 23-year-old man named Isaac Newton. Thin, quiet, obsessive, not yet famous, not yet certain of his path. He returned to his family's manor in Woolsthorpe, Lincolnshire, a small estate surrounded by apple orchards, and there alone, with nothing but time and his own restless mind, he began to think. What he thought about in those long, silent months would reshape humanity's understanding of the universe itself. There's a story told about Newton, one so famous, it's almost folklore now. You've probably heard it, the young man sitting beneath an apple tree, lost in thought, when suddenly thunk an apple falls and strikes him on the head. And in that moment, gravity is discovered. It's a nice story, simple, clean. The universe handing inspiration to genius on a silver platter. But the truth is quieter, stranger, and far more beautiful. Newton did see an apple fall. He mentioned it years later to friends casually, the way you might recall something small but pivotal from your youth. He was in the garden at Woolsthorpe. Yes, an apple did fall, but it didn't strike him. It simply dropped from branch to ground the way apples have fallen since the first tree bore fruit. And Newton, watching, asked himself a question that no one before him had thought to ask, in quite this way. Why did it fall straight down? Not, why did it fall? Everyone knew things fell. Heavy things dropped. That was obvious. That was nature. But why? Always down. Why? Always toward the center of the earth, what reached out from the ground and pulled the apple inward. And this is the moment that changed everything. Newton looked up at the moon, pale, distant, hanging motionless in the afternoon sky. The moon had been there his whole life, just as it had been there for every human who'd ever lived. It circled the earth month after month, never falling, never flying away. Everyone knew that too. But no one had asked why. Or rather, no one had imagined the answer might be the same as the apples. What if Newton wondered the moon was falling, not falling like the apple straight down to the ground, but falling the way a cannonball falls when fired fast enough, curving through space, dropping toward Earth, constantly, but moving forward fast enough that it never lands? What if the force that pulled the apple to the ground was the same force holding the moon in its orbit? It was an absurd idea. The apple fell because it was close, because it was heavy, because it was above the earth. But the moon was hundreds of thousands of miles away. How could the same force reach that far? And even if it could, why would the moon keep falling without ever getting closer? But Newton was a mathematician, and mathematics, he knew, didn't care about what seemed reasonable. It cared only about what the numbers said. So he began to calculate. He knew the moon's distance roughly 60 times the radius of the Earth, or about 240,000 miles. He knew the moon's orbital period, roughly 27 days. From that, he could calculate the moon's speed, and from the speed and the distance, he could figure out how fast the moon was falling toward Earth. Not falling in the sense of getting closer, falling in the sense of being pulled inward by gravity, the way the apple was pulled, but with so much sideways motion that the curve of its fall matched the curve of the Earth beneath it. The math was elegant, simple. The moon, moving at roughly 2,300 miles per hour in its orbit, was constantly accelerating toward Earth, pulled inward by gravity at a rate of about 1/20th of an inch per second every second. That acceleration was just enough to bend the moon's straight-line path into a circle. And here's what made Newton's insight so extraordinary. He realized that the strength of gravity had to weaken with distance. If the moon were closer to Earth, it would fall faster. If it were farther away, it would fall slower. The force diminished the farther you got from the source. How fast did it diminish? Newton calculated that too. He proposed what we now call the inverse square law. Gravity weakens with the square of the distance. If you double the distance, gravity becomes 4 times weaker. Triple the distance, and it's 9 times weaker. 10 times the distance, 100 times weaker. The moon, sitting 60 Earth radii away, experienced gravity that was 60 squared times weaker than the apple at Earth's surface. That's 3,600 times weaker. And yet, it was still enough. Still strong enough to hold the moon in its orbit. Strong enough to keep it falling forever, without ever letting it escape. Newton tested his math. He plugged in the numbers, the moon's distance, its speed, the radius of the Earth, the acceleration of falling objects on Earth's surface. And when he finished, when he checked his calculations against observation, the numbers matched. The moon was falling, just like the apple. The same force, the same law, operating across distances so vast they seem to erase meaning, yet precise enough to hold a celestial body in perfect orbit for billions of years. It's hard to overstate how radical this was. Before Newton, Earth and the heavens were separate realms. Earthly things, apples, stones, rain fell according to earthly rules. Celestial things, planets, moons, stars moved according to divine geometry. Perfect circles traced by perfect spheres, obeying laws that had nothing to do with falling stones or tumbling water. Aristotle had said so. The Church had agreed. For 2,000 years, that's simply how the universe worked. Newton erased the boundary. He said, there is no difference. The force that pulls an apple to the ground is the same force that holds the moon in orbit, that keeps the planets circling the sun, that governs the motion of every star and galaxy in the cosmos. One law, one force. Everywhere, always, forever. He called it universal gravitation, and he published it in 1687 in a book called Philosophia Naturalis, Principia Mathematica, mathematical principles of natural philosophy, often just called the Principia. It's one of the most important books ever written. In it, Newton laid out 3 laws of motion and 1 law of gravity, and from those 4 principles he derived the movements of the planets, the shape of Earth, the tides of the ocean, the wobble of the moon, the flattening of the poles, everything, from 4 ideas. But even Newton's genius had limits. He could describe gravity, how it worked, what it did, how strong it was at any distance, but he couldn't explain it. He didn't know what gravity was. He didn't know why masses attracted each other, why the force reached across empty space without any medium to carry it, why it obeyed the inverse square law and not some other pattern. In the Principia, he admitted as much. I have not yet been able to discover the cause of these properties of gravity from phenomena, he wrote, and I frame no hypotheses. He refused to guess. The math worked. The predictions matched reality. That was enough. But it bothered him. It bothered a lot of people. How could the Earth reach out across 93 million miles of empty space and pull on the sun? How could the sun pull back? There was nothing between them. No rope, no chain, no invisible hand. Just void. And yet the force was real, measurable, undeniable. For more than 200 years, scientists accepted Newton's law without understanding its mechanism. Gravity worked. That was all that mattered. It predicted eclipses, guided ships, explained tides, calculated orbits. Engineers used it to build bridges. Astronomers used it to discover planets Neptune found in 1846 by solving for the unseen mass that tugged Uranus off its predicted path. But the mystery remained. What is gravity? Not what does it do, but what is it? The answer would come from another young man sitting alone in a small apartment in Bern, Switzerland, working as a patent clerk scribbling equations during his lunch breaks. His name was Albert Einstein, and in 1915, he would propose something so strange, so counterintuitive, that even scientists who understood the math struggled to believe it. But that comes later. For now, we're still with Newton, still in that garden, watching the apple fall, looking up at the moon, and realizing for the first time that the two are falling the same way. It's worth pausing to appreciate what this means. Every child who's ever climbed a tree and let go feeling that brief moment of weightlessness, before the ground rushes up, they were performing the same experiment the moon performs every second of every day. The only difference is speed. The child drops straight down because they're not moving sideways. The moon curves through space because it is. But the falling, the pull, the inescapable tug of gravity, drawing everything toward everything else, that's the same. A child and a moon, an apple and a planet, all obeying the same law, all falling through space in ways that differ only in degree, not in kind. Newton's law also explained something that had puzzled astronomers for decades: why planets closer to the sun move faster in their orbits than planets farther out. Mercury, the innermost planet, screams around the sun in just 88 days. Earth takes 365. Jupiter takes nearly 12 years. Neptune, at the edge of the solar system, takes 165 years to complete a single orbit. Why? Because gravity weakens with distance. Neptune, sitting 30 times farther from the sun than Earth, feels the sun's pull 900 times weaker. So it doesn't need to move as fast to stay in orbit. It drifts slow and cold, tracing a path so wide that a single Neptunian year spans more than a human lifetime. And here's something beautiful that Newton's math revealed. If you know the mass of the sun and the distance to a planet, you can calculate exactly how fast that planet needs to move to stay in orbit. Not approximately. Exactly. The formula is simple velocity equals the square root of the gravitational constant times the sun's mass divided by the orbital radius. Plug in the numbers and out comes the speed. For Earth, that speed is 18.5 miles per second. For Neptune, it's 3.5 miles per second. The math works. Every time. For every planet, every moon, every asteroid, every object, circling every star in every galaxy. The same law playing out across the cosmos in infinite variation. Scientists now know that Newton's law of gravity is not the final answer. Einstein showed us that gravity is not a force at all, but a curvature of space-time, itself matter, bending the fabric of reality, and objects following the curves. We'll explore that soon. But Newton's insight remains foundational. His law is accurate enough to send spacecraft to Mars, to land robots on comets, to predict the return of Halley's Comet with precision measured in minutes across 76-year cycles. For most purposes, for most distances, Newton's gravity is all you need. And it all began with an apple and a question, and a young man alone in a garden, watching something fall and daring to imagine that the moon was falling too. Sometimes the universe reveals itself not in grand experiments or expensive telescopes, but in small moments. In the courage to ask why something obvious happens at all. In the willingness to see connections where others see only difference. Newton looked at an apple and saw the moon. He looked at the moon and saw the same rules that govern stones. He looked at the cosmos and saw not chaos, not divine whimsy, not separate realms operating under separate laws, but one universe united by mathematics, elegant and comprehensible. And because of that, we understand orbit. We understand falling. We understand why Earth doesn't crash into the sun, why the moon doesn't drift away, why the dance continues year after year, with a precision that seems almost too perfect to be real. But now we know the formula, the golden balance. And ahead we'll explore it in detail. The numbers, the distances, the speeds that make orbit possible. The exact combination of velocity and gravity that keeps a planet alive. 93 million miles. That's how far Earth sits from the sun. Not 92 million, not 94. 93 million miles, give or take a few thousand depending on where we are in our orbit, and 18.5 miles per second. That's how fast we move through space. Not 18, not 19. 18.5 miles per second, or 67,000 miles per hour, traced with such precision that we complete our orbit within minutes of the same time every year. These two numbers, distance and velocity, are not random. They are bound together by mathematics so exact, so unforgiving, that if either one changed by even a small percentage, everything we know would unravel. This is the golden formula, the perfect balance. And understanding it means understanding why Earth has remained habitable for 4.5 billion years. Let's start with something simple. Imagine you're swinging a bucket of water over your head, fast enough that the water doesn't spill out, even when the bucket is upside down. You've probably done this, or or seen it done. The water stays inside, pressed against the bottom of the bucket by the motion itself. Now, imagine you slow down. Not much, just a little. What happens? The water sloshes. It starts to spill. Slow down more and it pours out completely. The motion wasn't fast enough to keep it in place. That's orbit in miniature. Earth is the water. The sun's gravity is your arm pulling inward. And our velocity at 18.5 miles per second is the speed of the swing. Too slow and we spill inward toward the sun. Too fast and we break free, flying outward into the cold. But at exactly this speed, at exactly this distance, the forces balance. Not because something is pushing us outward, not because we're resisting, but because falling at this speed from this distance creates a curve that matches the curvature of space itself. Scientists call this orbital velocity, and there's a precise formula for it. The velocity needed to orbit any object depends on two things: the mass of the object you're orbiting and your distance from it. Nothing else matters. Not your own mass, not your shape or composition. Just those two numbers, how heavy the thing you're circling is and how far away you are. For Earth orbiting the sun, the math looks like this: the sun's mass is approximately 2 times 10 to the power of 30 kilograms. That's a 2 followed by 30 zeros, an almost incomprehensible number. Earth's average distance is 150 million kilometers, or 93 million miles. Plug those into Newton's formula, and out comes the speed 29.78 kilometers per second, 18.5 miles per second. That's not an approximation. That's the number. That's the speed. We're actually moving. Measured by spacecraft, confirmed by observation, predicted by math that's been tested for more than 300 years. And here's what makes it beautiful. If Earth were closer to the sun, we'd need to move faster to stay in orbit. If we were farther away, we'd move slower. The relationship is precise, mathematical, inescapable. Venus, for example, sits about 67 million miles from the sun, closer than Earth. To maintain orbit at that distance, Venus must travel at 35 kilometers per second, or roughly 78,000 miles per hour. That's faster than Earth. It has to be. The sun's gravity is stronger there, pulling harder, demanding more speed to avoid falling inward. Mars sits farther out, about 142 million miles from the sun. At that distance, the sun's pull is weaker. Mars only needs to travel at 24 kilometers per second, or 54,000 miles per hour to maintain orbit, slower than Earth, calmer, drifting through space with less urgency because the hand of gravity holds more gently at that distance. The pattern holds everywhere. Mercury scorched in close races at 48 kilometers per second. Saturn cold and distant glides at 9.6 kilometers per second. Neptune at the edge of the solar system crawls through its orbit at just 5.4 kilometers per second, barely 1/6 Earth speed. The formula works. Every time. For every planet, every moon, every asteroid belt, every ring of debris circling every star. The universe doesn't negotiate. It doesn't adjust for special cases. If you want to orbit at a given distance, you must move at a specific speed. No faster, no slower. Exactly that speed, or the orbit, fails. But what happens if the speed changes? What if something, a collision, a gravitational interaction, a change in the sun's mass altered Earth's velocity? By just 10%, scientists have run the simulations. The results are not comforting. If Earth's velocity suddenly increased by 10% from 67,000 miles per hour to 74,000, we would no longer be moving at orbital velocity for our current distance. We'd be moving too fast. The sun's gravity wouldn't be strong enough to hold us in a circular path. Our orbit would stretch, becoming more elliptical, carrying us farther from the sun with each pass. Over time, our average distance from the sun would increase. Not dramatically, perhaps, to 160 or 170 million miles instead of 150. That's only a 10 or 15% increase, but it would be enough. At that distance, the amount of sunlight reaching Earth would drop by roughly 20%. Winters would last longer. Summers would be cooler. Ice caps would expand, creeping southward and northward, reflecting more sunlight back into space, cooling the planet further in a feedback loop that scientists call a runaway glaciation event. Eventually, within a few thousand years, Earth could become a snowball, frozen solid from pole to pole, with only a thin band of liquid water remaining near the equator, if any at all. And if our velocity decreased by 10%, if we slowed to 60,000 miles per hour instead of 67,000, the opposite catastrophe. At that slower speed, we'd be moving too slowly to maintain our current orbit. Gravity would pull us inward, not immediately, not in a sudden plunge, but gradually, over millions of years, our orbit would decay. Each year, we'd drift a little closer to the sun. The distance would shrink from 93 million miles to 85 million, then 80, then 75. And as we approached, the sun's warmth would intensify, not by a little, by a lot. The amount of energy Earth receives from the sun follows the inverse square law, just like gravity. Move 10% closer, and the energy increases by more than 20%. Move 20% closer, and it increases by nearly 50%. The oceans would warm. Ice caps would melt. Sea levels would rise. But that's just the beginning. As temperatures climbed, the oceans would begin to evaporate faster, releasing water, vapor, into the atmosphere. And water vapor is a greenhouse gas, one of the most powerful. It traps heat. The more water in the air, the hotter the planet becomes. The hotter the planet, the more water evaporates. Another feedback loop, another runaway process. Scientists call this a runaway greenhouse effect, and we've seen it happen. Venus, our sister planet, likely experienced this billions of years ago. Once some researchers suggest Venus may have had oceans, but the planet sits too close to the sun, just close enough that the heat triggered runaway evaporation. The oceans boiled away. The atmosphere thickened with carbon dioxide and water vapor. Surface temperatures rose to 860 degrees Fahrenheit, hot enough to melt lead. Today, Venus is a hell world. Dry, scorched, hostile to any life we can imagine. That's what 10% slower would cost us. Not immediately, not in our lifetimes. But over the long arc of planetary time, the balance would break, and Earth would slide toward one extreme or the other, frozen or burning, depending on which way the speed changed. The fact that we're still here, still orbiting at exactly the right speed, tells you something profound about the stability of the solar system. For 4.5 billion years, nothing has disrupted our velocity enough to matter. No rogue planet has passed close enough to knock us off course. No massive asteroid has struck with enough force to slow or accelerate our orbit significantly. The solar system, despite its apparent chaos, comets streaking asteroids, tumbling planets wobbling slightly on their axes, has remained remarkably stable. But that stability is not guaranteed. It's not a law of nature. It's simply luck. Or perhaps more accurately, it's a consequence of survival bias. We're here orbiting peacefully because our orbit happened to be stable. Any system that wasn't stable, any planet that drifted too close or flew too far, either burned, froze, or was ejected into interstellar space long ago, leaving only the balanced ones behind. NASA scientists understand this better than most. When they send spacecraft to other planets, they have to calculate orbital velocities with absurd precision. The Parker Solar Probe, launched in 2018 to study the Sun, had to be slowed down dramatically, not sped up to fall closer to the Sun. It sounds counterintuitive. If you want to get closer to the Sun, shouldn't you fly toward it? No, because we're already orbiting, already moving at 18.5 miles per second around the Sun. To fall inward, you have to slow down. You have to shed velocity, dropping below orbital speed, so gravity can pull you into a tighter curve. Parker Solar Probe used Venus's gravity to do this. It swung past Venus 7 times each pass, stealing a little of the spacecraft's orbital speed, lowering it bit by bit into closer and closer passes around the Sun. By 2024, Parker had reached a distance of just 4 million miles from the Sun's surface, close enough to touch the corona, the Sun's outer atmosphere, where temperatures exceed 1 million degrees. And to survive that close approach, Parker had to be moving fast, very fast. At its closest point, the spacecraft races at 430,000 miles per hour, more than 6 times faster than Earth's orbital speed, because the closer you are, the faster you must move to avoid falling in. That's the paradox of orbit. To go deeper into a gravity well, you must first slow down. But once you're deeper, you must move faster to stay there, slow to descend, speed to survive. It's a dance of contradictions, balanced on the edge of mathematics. And Earth performs this dance without thinking, without choosing. We are locked into our speed by the momentum of our formation, by the angular velocity inherited from the spinning disk of gas and dust that collapsed to form the Sun and planets 4.5 billion years ago. That disk was already rotating. When it collapsed, the rotation accelerated the same way a figure skater spins faster when they pull their arms inward. By the time Earth coalesced from the debris, we were already moving at roughly the speed we move now. And because space is a vacuum, because there's no air to slow us down, no friction to steal our momentum, that speed has remained essentially unchanged for billions of years. The only thing that could change it significantly would be a close encounter with another massive object, a rogue planet passing through the solar system, a star drifting too close, a black hole wandering into our neighborhood. These events are possible, but vanishingly rare. The distances between stars are so vast, the odds of a collision so small, that most solar systems, including ours, go billions of years without any significant disruption. And so we continue. 93 million miles out, 18.5 miles per second, falling and falling endlessly in a curve so perfect it seems drawn by an invisible hand. But the curve is not quite perfect. It's not a circle. And that small imperfection, that gentle stretching of the orbit into an ellipse, reveals something deeper about the way gravity works, something Johannes Kepler discovered 400 years ago by staring at Mars through a telescope and refusing to accept the perfect circles everyone else believed in. That's where we're drifting next, to the shape of the orbit itself, to the ellipse, to the realization that Earth does not stay 93 million miles from the Sun at all times, that we swing closer, then farther closer, then farther, in a rhythm that has nothing to do with the seasons and everything to do with the ancient geometry of falling bodies. Right now, in early December, Earth sits approximately 91.5 million miles from the Sun. But in early July, the middle of summer, for those in the Northern Hemisphere, will be 94.5 million miles away, 3 million miles farther, in summer, when the days are longest and the heat is strongest. That seems wrong, doesn't it? If we're farther from the Sun, in summer, shouldn't we be colder, not warmer? The answer reveals something beautiful and unexpected about the shape of our orbit and about the difference between distance and tilt, between geometry and seasons, between what seems obvious and what is actually true. For most of human history, scientists assumed orbits were perfect circles. It made sense. Circles were divine, perfect, unchanging. The Greek philosopher Plato, around 380 BC, declared that heavenly bodies must move in circles because circles were the most perfect shape, and the heavens could be nothing less than perfect. Aristotle agreed. So did Ptolemy. So did Copernicus, even as he moved Earth from the center of the cosmos to a position orbiting the Sun. He kept the circles, changed the center, preserved the shape, because circles felt right, symmetrical, eternal. But there was a problem. The observations didn't quite match. Mars in particular moved strangely. Sometimes it appeared brighter closer, sometimes dimmer farther. Its speed through the sky varied. It didn't behave like something moving in a perfect circle at constant velocity. Astronomers tried to fix this by adding smaller circles, epicycles. They called them circles, within circles, wheels turning on wheels, each one carefully tuned to match the observations. Ptolemy's model, finalized around 150 AD, used dozens of epicycles to explain planetary motion. It was complicated, inelegant, but it worked more or less. Then came Johannes Kepler, a German mathematician and astronomer, born in 1571, obsessive and brilliant and willing to question everything. Kepler inherited something precious, decades of observations recorded by the Danish astronomer Tycho Brahe, the most precise measurements of planetary positions anyone had ever made accurate to within 1 arc-minute, 1/60th of a degree. Brahe had spent his life watching the sky, night after night, without a telescope. They hadn't been invented yet, using only naked-eye observations and enormous instruments he'd built himself. When he died in 1601, his data passed to Kepler, who spent the next 8 years trying to make sense of Mars. 8 years? Staring at numbers, drawing circles, calculating speeds, and nothing worked. No matter how carefully Kepler adjusted the circles, no matter how many epicycles he added, the predictions were always slightly off. Just a little, just enough to matter. Most scientists would have blamed the data, would have assumed the observations were flawed, that the instruments weren't precise enough, that the errors were inevitable. But Kepler trusted Bra. He knew the observations were good, which meant the problem wasn't the data. It was the theory. So Kepler did something radical. He abandoned the circle. After 2,000 years of assumption, after centuries of philosophers and theologians insisting that the heavens moved in perfect curves, Kepler looked at the numbers and said, what if they don't? What if orbits aren't circles at all? In 1609, he published his answer in a book called Astronomy Nova, New Astronomy. In it, he proposed what we now call Kepler's first law. Planets move in ellipses, not circles with the sun at one focus. An ellipse is like a stretched circle. Instead of one center point, it has two focus points. Draw an ellipse by placing two pins in a board, looping a string around them, pulling the string taut with a pencil, and drawing the curve. The farther apart, the pins, the more stretched the ellipse. The closer together, the more it resembles a circle. Earth's orbit is an ellipse. Not a dramatic one, it's very close to circular, with an eccentricity of just 0.0167. That's a measure of how stretched the ellipse is, where 0 is a perfect circle and 1 is a line. Earth's ellipse is stretched by less than 2%, but that small stretch makes a difference. At perihelion, the closest point to the sun, which occurs around January 3rd each year, Earth sits about 91.4 million miles from the sun. At aphelion, the farthest point around July 4th, we're 94.5 million miles away. That's a difference of roughly 3 million miles. About 1.7% closer in January, 1.7% farther in July. And yes, that means Earth is closest to the sun in the middle of winter for the northern hemisphere and farthest during summer. The seasons have nothing to do with distance. They're caused by Earth's axial tilt, the 23.5-degree angle. Our planet leans relative to its orbit. When the northern hemisphere tilts toward the sun, it's summer there, regardless of distance. When it tilts away, it's winter. Distance matters, but not as much as you'd think. The 3 million miles between perihelion and aphelion changes the amount of sunlight Earth receives by about 6.5%. That sounds significant, but it's spread across the entire planet, averaged over the whole year. The tilt of the axis, by contrast, concentrates sunlight at different latitudes depending on the season, creating differences of more than 50% in solar energy between summer and winter at higher latitudes. So tilt wins. Tilt creates seasons. Distance creates a small variation in Earth's overall energy budget, but it doesn't determine whether you need a coat. But here's what's fascinating. Earth's speed changes as we move through the ellipse. We don't travel at a constant velocity. We speed up as we approach the sun and slow down as we move away. This was Kepler's second law, published in the same book. A line drawn from the sun to a planet sweeps out equal areas in equal times. That sounds abstract, but it means something simple. When Earth is closer to the sun at perihelion, we move faster, about 30.3 kilometers per second. When we're farther away at aphelion, we slow to 29.3 kilometers per second. A difference of about 1 kilometer per second, or roughly 2,000 miles per hour. Why? Because of the conservation of angular momentum. It's the same reason figure skaters spin faster when they pull their arms inward. As Earth swings closer to the sun, We trade distance for speed. As we drift farther, we trade speed for distance. The total angular momentum, a product of mass velocity and distance, remains constant. So if distance decreases, velocity must increase. If distance increases, velocity must decrease. This was a revolutionary insight. It meant that planetary motion wasn't uniform, wasn't steady. The heavens didn't move like clockwork, with every moment identical to the last. They moved like dancers, speeding and slowing in rhythm with gravity, each planet tracing its own tempo through the cosmic waltz. And Kepler found one more law. His third law, published 10 years later in 1619, the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. In simpler terms, the farther a planet is from the Sun, the longer its year, and the relationship is mathematical, precise, predictable. Earth at 1 astronomical unit, 93 million miles, takes 1 year to orbit Mars. At one point, 5 astronomical units takes 1.88 years. Jupiter, at 5.2 astronomical units, takes 11.86 years. The numbers fit perfectly. Plug in the distance and you can predict the orbital period, or measure the period and calculate the distance. The math works both ways. Newton would later show that Kepler's laws were consequences of universal gravitation, that the ellipse, the changing speed, the relationship between distance and period, all emerged naturally from the inverse square law of gravity. Kepler had discovered the pattern. Newton explained why the pattern existed. Together, they gave us a complete picture of orbital mechanics. But back to the ellipse. Why does it matter that Earth's orbit isn't circular? Because it reminds us that nature doesn't care about our aesthetics. We prefer circles. We find them satisfying, complete, perfect. But the universe operates on physics, not preference. Orbits are ellipses because that's what gravity creates when objects move through space. Sometimes the ellipse is almost circular, like Earth's. Sometimes it's wildly stretched, like Halley's Comet, which swings from just inside Venus's orbit all the way out beyond Neptune, tracing an eccentricity of 0.967, nearly a straight line. Mercury has the most eccentric orbit of the major planets, 0.206. At perihelion, it sits 29 million miles from the Sun. At aphelion, 43 million. A difference of 14 million miles, or nearly 50%. That extreme variation creates temperature swings of more than 1,000 degrees Fahrenheit between Mercury's day side and night side. The planet bakes and freezes in cycles so violent that lead would melt on the surface during the day and solidify at night. Pluto's orbit is even stranger, tilted 17 degrees relative to the plane most planets follow, and so elliptical that for part of its 248-year orbit, Pluto actually passes inside Neptune's orbit, becoming temporarily the 8th planet instead of the 9th. Between 1979 and 1999, Pluto was closer to the Sun than Neptune. Then it swung back out into the dark and won't return to that inner position for another 200 years. These ellipses aren't random. They're shaped by gravitational interactions. Every planet tugs on every other planet, gently, constantly perturbing orbits over millions of years. Jupiter, the most massive planet, has the strongest influence. Its gravity shepherds asteroids, ejects comets, and subtly nudges the orbits of the inner planets, including Earth. Scientists have calculated that Jupiter's presence likely prevented a planet from forming in the asteroid belt between Mars and Jupiter. The region had enough material, enough dust and rock to coalesce into a world. But Jupiter's gravity stirred the belt, accelerating collisions, preventing the fragments from clumping together. Instead of a planet, we got rubble millions of asteroids tumbling through space. Remnants of what could have been. Jupiter also protects Earth. Its immense gravity acts like a cosmic vacuum cleaner, attracting comets and asteroids that might otherwise strike the inner solar system. Some estimates suggest that without Jupiter, Earth would experience impacts from large asteroids 10 to 100 times more often. Life might never have had the stable environment needed to evolve beyond simple microbes. So the ellipse isn't just geometry, it's history. It's the memory of every gravitational tug, every near miss, every interaction since the solar system formed. Earth's nearly circular orbit tells a story of stability of a solar system that settled into balance and stayed there, allowing 4.5 billion years of relative peace. But that peace isn't permanent. Orbits change, slowly, imperceptibly. But they do change. Earth's eccentricity varies over cycles of about 100,000 years, driven by gravitational interactions with Jupiter and Saturn. Sometimes our orbit is more circular, like it is now. Sometimes it stretches a bit more, reaching eccentricities of 0.05 or higher. These changes affect Earth's climate. When the orbit is more elliptical, the difference between perihelion and aphelion increases, amplifying seasonal contrasts. When combined with shifts in axial tilt and the precession of Earth's rotational axis, these orbital variations drive long-term climate cycles, ice ages, and warm periods that come and go over tens of thousands of years. Scientists call these Milankovitch cycles, named after Serbian scientist Milutin Milankovitch, who calculated them in the 1920s. He showed that small changes in Earth's orbit and tilt could explain the ice ages that carved valleys and shaped continents over the past 2 million years. His work was controversial. At first, two subtle critics said too gentle to create such dramatic effects. But the evidence proved him right. Ice cores drilled from Antarctica and Greenland showed temperature patterns that match his predictions almost perfectly. So Earth's ellipse isn't just an abstract shape traced in space. It's a living, breathing part of our climate system, a factor in ice ages, a variable in the equation of habitability, and a reminder that even stable orbits are not truly static. They shift, they breathe, they respond to forces both internal and external evolving over timescales, so long that human lifetimes vanish into irrelevance. But for now, for this moment, the ellipse is gentle. The eccentricity is low. The orbit is nearly circular. And we drift through space in a path so smooth, so predictable, that we can calculate our position 1,000 years into the future, with accuracy measured in seconds. That precision, that predictability comes from understanding the true shape of the orbit. Not the perfect circle we wished for, but the gentle ellipse that actually exists. And from that understanding, we've built spacecraft, predicted eclipses, and learned to see the solar system not as a fixed clockwork, but as a dynamic dance, ancient, elegant, and impossibly precise. Yet even this understanding was incomplete, because Newton's gravity, as powerful as it was, as accurate as it remains for most purposes, missed something fundamental. Something Einstein would reveal in 1915 when he showed that gravity itself was not a force at all, but a curvature, a bending of the very fabric of space and time. Imagine you're standing on a trampoline, flat, taut, stretched perfectly horizontal. Now imagine someone rolls a bowling ball onto that trampoline. What happens? The fabric dips, curves, creates a depression where the ball rests. And if you roll a marble across the trampoline, now it doesn't travel in a straight line anymore. It curves toward the bowling ball, following the slope created by the weight. That's not gravity exactly, but it's the closest most of us will ever come to visualizing what Albert Einstein discovered in 1915, that gravity is not a force pulling objects together, but a curvature of space itself, and objects simply follow the curves. For more than 200 years, Newton's law of gravity had worked perfectly. It predicted planetary orbits, explained tides guided ships, discovered Neptune. But there was one small problem, one tiny discrepancy that no one could explain. Mercury's orbit wasn't quite right. Not dramatically wrong. Just slightly off. Mercury, the closest planet to the Sun, orbits in an ellipse as all planets do. But the ellipse itself rotates the point of closest approach. The perihelion shifts slowly over time, tracing a pattern called precession. Imagine an ellipse spinning like a spirograph, with the Sun at one focus, and the ellipse itself gradually rotating around that focus. Astronomers had measured this precession. Mercury's perihelion advances by about 5,600 arcseconds per century. That's a tiny amount, about 1.5 degrees per century. But it's measurable, predictable, observable. Newton's gravity could account for most of it. The gravitational pull of Venus, Earth, Jupiter, and the other planets tugged on Mercury, perturbing its orbit, causing most of that precession, but not all of it. When astronomers calculated the effect of every known planet, every gravitational interaction, they could only explain 5,557 arcseconds per century. 43 arcseconds remained unexplained, roughly 1/100th of a degree per century. A difference so small, it should have been meaningless. But it wasn't meaningless. It was real, measurable, persistent, and no one knew why. Some astronomers proposed a hidden planet between Mercury and the Sun. They even named it Vulcan, tugging on Mercury with its unseen gravity. Searches were conducted. Telescopes pointed sunward during eclipses, hoping to catch a glimpse of the missing world. But nothing was ever found. Vulcan didn't exist. The discrepancy remained. A whisper in the data, a crack in the foundation of physics. Then came Einstein. Born in 1879 in Germany, he was working as a patent clerk in Switzerland when he published his theory of special relativity in 1905. That theory revolutionized our understanding of space and time, showing that they were not separate fixed entities, but interconnected, a four-dimensional fabric called space-time, where measurements of distance and duration depended on the observer's motion. But special relativity only worked for objects moving at constant velocity. It couldn't handle acceleration, and it couldn't explain gravity. For the next 10 years, Einstein struggled to extend his theory. He knew gravity had to fit into space-time somehow, but he couldn't see how. Then, in 1907, he had what he later called the happiest thought of my life. He imagined a man falling from a roof. While falling, The man would feel weightless, no sensation of gravity at all. If he dropped a ball, it would fall beside him at the same rate, appearing to float. Einstein realized that free fall and floating in deep space felt identical. There was no experiment the falling man could perform to tell the difference between falling in a gravitational field and drifting weightless in empty space. Gravity, Einstein concluded, wasn't a force you could feel. It was something deeper, something woven into the structure of space-time itself. Over the next 8 years, Einstein developed the mathematics to describe this insight. He called it general relativity, and he published it in November 1915 in a series of papers presented to the Prussian Academy of Sciences in Berlin. The core idea was simple, even if the math was not mass curves space-time. And objects moving through space-time follow the straightest possible paths. Geodesics mathematicians call them through that curved space. What looks like gravitational attraction is actually objects following the natural geometry of a universe warped by mass. The sun, with its enormous mass, creates a deep curve in space-time around it. Earth, moving through that curved space, follows a geodesic, a path that looks curved from the outside but feels straight to Earth itself. We're not being pulled toward the sun by a mysterious force. We're simply moving forward through space that happens to be curved, and that curvature guides us into an orbit. It's like walking in a straight line on the surface of a sphere. From your perspective, you're going straight. But from above, an observer sees you tracing a circle around the planet. The path is curved because the space you're walking through is curved. That's orbit. That's gravity. Not a pull, not a force, just geometry. Einstein's equations predicted everything Newton's had, plus a little more. And one of those little more predictions was the precession of Mercury's perihelion. When Einstein applied his equations to Mercury's orbit, accounting for the curvature of space-time near the sun, the math naturally produced an extra 43 arcseconds of precession per century. Exactly 43. Precisely the missing amount, with no hidden planets, no adjustments, no epicycles, just the natural consequence of moving through curved space-time. When Einstein completed this calculation in November 1915, he later said his heart palpitated as if something inside him had snapped. He'd found the answer. The discrepancy that had haunted astronomers for decades vanished the moment gravity became geometry. But Einstein needed more than Mercury to prove his theory. He needed a test, a prediction that Newtonian gravity couldn't make something only general relativity would produce something observable, dramatic, undeniable. He found it in starlight. Einstein's equations predicted that light itself would bend when passing near a massive object, not because light has mass. It doesn't in the traditional sense, but because light travels through space-time. And if space-time is curved, light follows the curve. Imagine shining a flashlight across the trampoline with a bowling ball on it. The light doesn't curve in reality. Of course, air isn't space-time. But in the universe, light passing near the sun would follow the curvature created by the sun's mass, bending its path slightly toward the sun. Newton's gravity also predicted a tiny bending of light, treating photons as if they had a small effective mass. But Einstein's general relativity predicted twice as much bending. If you could measure the deflection of starlight passing near the sun, you could distinguish between Newton and Einstein. you could test which view of gravity was correct. There was one problem: the sun is bright. Far too bright to see stars near it during the day. The only time you could observe stars close to the sun's edge was during a total solar eclipse, when the moon blocks the sun's disk, revealing the stars beyond. And so, astronomers waited for an eclipse. 1919 brought one visible from West Africa and South America on May 29th. A British expedition led by astronomer Arthur Eddington traveled to the island of Principe off the coast of Africa to observe it. Another team went to Sobral, Brazil. The weather was uncertain. Clouds threatened. But during the eclipse, as the moon's shadow swept across the earth and day became night, Eddington's team captured photographs of the stars around the sun. They measured the positions of those stars and compared them to their known positions when the sun wasn't nearby, taken months earlier. The starlight had bent. Not by much, about 1.7 arc seconds, roughly the width of a quarter, seen from 2 miles away. But it was measurable, and the amount of bending matched Einstein's prediction almost perfectly. On November 6, 1919, the results were announced at a joint meeting of the Royal Society and the Royal Astronomical Society in London. Newton's law of gravity, unchallenged for 232 years, had been superseded. Gravity was not a force. Gravity was the shape of space itself. The headline in the London Times the next day read, "Revolution in Science New Theory of the Universe, Newtonian Ideas Overthrown." Einstein became an international celebrity overnight. His name became synonymous with genius, and general relativity became the new foundation of physics. But what does this mean for Earth's orbit? If gravity is geometry, what keeps us circling the sun? The answer is the same as before, but deeper. Earth moves forward through space at 18.5 miles per second. That's our momentum, inherited from the formation of the solar system. The sun's mass curves space-time around it, creating what physicists call a gravity. Well, a depression in the fabric of space, steep near the sun, gentler farther out. Earth moving through this curved space follows the straightest possible path. To us, orbiting feels like moving in a straight line, because we can't perceive the curvature. But from outside, from a higher dimension, looking down on the fabric of space-time itself, we're tracing a curve, a geodesic, that loops endlessly around the sun, guided not by a force, but by the geometry of the universe itself. Think of it like a marble rolling around the inside of a bowl. The marble isn't being pulled by a force. It's following the natural slope of the surface, guided by the shape beneath it. If the bowl were perfectly smooth and the marble had no friction, it would roll forever, tracing circles or ellipses depending on its speed and angle. Earth is the marble. Space-time is the bowl. And the sun's mass creates the slope. General relativity also explains why time runs differently at different distances from a massive object. Clocks closer to the sun tick slightly slower than clocks farther away. The difference is tiny, about 1 part in 100 billion for Earth's distance. But it's real. It's measurable. And it's essential for technologies like GPS. GPS satellites orbit about 12,000 miles above Earth's surface, where space-time is slightly less curved than at ground level. Because of that, time on the satellites runs faster than time on the ground, about 45 microseconds faster per day. If GPS calculations didn't account for this relativistic effect, the system would drift out of alignment by about 6 miles per day. Within a week, your navigation would be useless. So every time you use GPS to find your way, you're relying on Einstein's insight from 1915. You're relying on the fact that gravity is geometry, that time bends near mass, and that clocks tick at different rates, depending on where they sit in the curved fabric of space-time. This is the universe we live in, not the one Newton described with invisible forces reaching across space, pulling objects together by mysterious action at a distance, but Einstein's universe, a universe where matter tells space how to curve and space tells matter how to move. A universe where falling is simply following the shape of space itself. And yet, for almost everything we do, Newton's law is still accurate enough. The difference between Newtonian gravity and Einsteinian gravity only becomes significant near very massive objects, black holes, neutron stars, the sun's immediate vicinity, or when measuring with extraordinary precision over long times. For launching spacecraft, predicting eclipses, calculating tides, Newton's equations work beautifully. They're simpler, easier to use, and accurate to within a fraction of a percent for most purposes. It's only when you need that last fraction, that final precision, that Einstein's equations become necessary. But the conceptual shift matters. Understanding that gravity is geometry, not force, changes how we think about the cosmos. It reveals that space and time are not just a stage where events happen, but active participants in the drama, flexible, dynamic, responsive to mass and energy. It also opens doors to phenomena Newton's gravity could never explain. Black holes where space-time curves so steeply that even light cannot escape. Gravitational waves ripples in space-time itself, spreading outward from colliding black holes or neutron stars at the speed of light. The expansion of the universe, driven not by objects moving through space, but by space itself stretching. All of this comes from Einstein's insight, from the realization that what we call gravity is simply the shape of the universe, and what we call orbit is simply the natural path objects trace through that shape. And Earth traces its path beautifully, smoothly, following the curvature laid down by the sun's mass, held in place not by chains or forces or invisible hands, but by geometry alone. We fall through curved space endlessly gracefully, without ever needing to know that space is curved at all. But even this elegant balance is not immune to disruption. Even curved space-time can be disturbed by events beyond our control, wandering stars, rogue planets, the slow evolution of the sun itself. And understanding what could change our orbit means understanding just how fragile or how resilient our position in space really is. 4.5 billion years. That's how long Earth has maintained its orbit around the sun, 93 million miles out, circling once per year, tracing the same elliptical path, generation after generation, epoch after epoch, with a consistency that feels eternal. But what if it isn't? What if the stability we take for granted is more fragile than it appears? What could disrupt our orbit, knock us closer to the sun, or fling us into the darkness beyond? The answer might surprise you, because the threats aren't hypothetical. They're real, and some of them have already happened. Space feels empty, vast, silent, safe. But it's not as empty as we imagine. The solar system is crowded with wandering objects, asteroids, comets, rogue planets ejected from other star systems, even stars themselves passing within gravitational range. And every one of them carries the potential to disturb the delicate balance that keeps Earth alive. Let's start with the most dramatic possibility: a rogue planet passing through the inner solar system. Rogue planets are real. Astronomers have discovered dozens of them. Massive worlds drifting alone through interstellar space, untethered to any star, ejected from their birth systems by gravitational interactions, millions or billions of years ago. Some estimates suggest there may be more rogue planets in the Milky Way than stars, perhaps 2 trillion of them, wandering the galactic darkness invisible, except when they pass in front of distant stars and briefly block the light. Most of these rogues drift harmlessly, far from Earth, separated by distances measured in light years. But occasionally, very occasionally, one might pass near our solar system. And if it did, if a Jupiter-sized rogue planet wandered within a few astronomical units of the Sun, its gravity would tug on every planet in the system. Scientists have modeled this scenario using computer simulations. The results are unsettling. A rogue planet passing through the inner solar system wouldn't need to collide with Earth to destroy us. It wouldn't even need to come particularly close. Just passing within 1 or 2 astronomical units, say between Earth and Mars, would be enough to gravitationally perturb our orbit. The effect would depend on the rogue's mass speed and trajectory. But in many simulations, Earth's orbital velocity changes by several percent. Sometimes we're accelerated, flung into a wider orbit, where temperatures drop and ice ages become permanent. Sometimes we're slowed spiraling inward toward the sun over thousands of years, until the oceans boil. And in some scenarios, the worst ones, our orbit becomes so elliptical, so stretched, that we swing wildly between scorching heat and freezing cold with each pass, making stable climate impossible. How likely is this not? Very. The odds of a rogue planet passing close enough to matter are extraordinarily small, perhaps, once every few billion years. If that, the distances between stars are so vast, the spaces between solar systems so empty, that most rogues travel for billions of years without encountering anything at all. But extraordinarily small is not 0. And over the lifetime of a planet, even rare events eventually happen. There's evidence that something like this may have occurred early in the solar system's history. Between 4.1 and 3.8 billion years ago, Earth and the Moon were bombarded by an unusually high number of asteroids and comets, an event called the Late Heavy Bombardment. The Moon's surface still bears the scars, vast impact basins, like Mare Imbrium, Mare Serenitatis, Mare Crisium, each one the result of a collision with an object hundreds of miles across. What caused this sudden surge in impacts? One theory suggests that the orbits of Jupiter and Saturn shifted during this period, destabilizing the asteroid belt and the Kuiper belt, sending millions of objects careening into the inner solar system. Another theory proposes that a passing star, or even a rogue planet, disturbed the Oort cloud, a vast shell of icy bodies surrounding the solar system at a distance of about 1 light-year, sending a storm of comets sunward. We don't know for certain. The evidence is sparse, the timescales enormous. But we know it happened. We know Earth survived bombardment intense enough to reshape the Moon's surface. And we know that whatever caused it, the event was tied to gravitational instability somewhere in the solar system. Jupiter, in fact, plays a dual role in Earth's safety. On one hand, its immense gravity shields us. Jupiter acts as a gravitational vacuum cleaner, attracting comets and asteroids that might otherwise threaten Earth. In 1994, astronomers watched as Comet Shoemaker Levy 9 broke apart and crashed into Jupiter in a series of spectacular impacts, each one releasing energy equivalent to millions of nuclear bombs. If that comet had struck Earth instead, it would have been catastrophic. But Jupiter's gravity also destabilizes. It perturbs asteroid orbits, occasionally sending them inward. It influences the eccentricity of Earth's orbit over tens of thousands of years. And during the solar system's youth, when planetary orbits were still settling, Jupiter's migrations may have ejected entire planets, hypothetical worlds that once orbited between Mars and Jupiter, or beyond Neptune, now lost to interstellar space. Some models suggest the solar system originally had 5 gas giants, not 4. The fifth, perhaps as large as Uranus or Neptune, was flung outward by a close encounter with Jupiter escaping the Sun's gravity entirely and becoming one of the galaxy's countless rogue planets. If true, that lost world is still out there, drifting cold and alone through the darkness, a remnant of our own system's chaotic past. Closer to home, there's another threat: asteroids. Not the small ones that burn up in Earth's atmosphere as meteors, but the large ones, the mountain-sized ones, the ones capable of altering orbits. An asteroid impact wouldn't change Earth's orbit directly. Even a 10-mile wide asteroid has far too little mass compared to Earth to make a difference. But impacts can change Earth's rotation, its axial tilt, even the distribution of mass on the surface. And over long timescales, those changes can subtly influence the gravitational interactions between Earth and the Moon, which in turn affect Earth's orbital stability. The impact that killed the dinosaurs 66 million years ago, a 6-mile wide asteroid striking what is now the Yucatan Peninsula, released energy equivalent to 10 billion Hiroshima bombs. It vaporized rock, created tsunamis, ignited wildfires, and threw so much dust into the atmosphere that sunlight dimmed for years. But it didn't change Earth's orbit. Our velocity remained the same, our distance from the sun unchanged. The impact was catastrophic for life, but cosmically insignificant. However, there's a theoretical limit. If an asteroid were large enough, perhaps 100 miles across, or if multiple impacts occurred in rapid succession, the cumulative effect could alter Earth's angular momentum enough to shift our orbit by a small but measurable amount. Such objects are rare. The largest asteroids in the belt, Ceres Vesta Pallas, are hundreds of miles across, but their orbits keep them safely distant. Still, in the deep past, during the solar system's formation, collisions with objects this size were common. Earth itself formed from countless collisions. Our moon was born from a Mars-sized planet called Theia, crashing into the young Earth 4.5 billion years ago. That impact didn't destroy Earth's orbit. Instead, it stabilized it. The moon acts as a gravitational anchor, slowing Earth's rotation, stabilizing our axial tilt, creating tides that helped life evolve. Without the moon, Earth would wobble chaotically its tilt, varying by tens of degrees over millions of years, creating climate instability that might have prevented complex life from arising. So, collisions can be both destructive and constructive. The universe doesn't care which. It only follows the mathematics of momentum and gravity. There's another slower threat one that's happening right now. The sun is losing mass. Every second, the sun converts roughly 4 million tons of matter into energy through nuclear fusion, radiating that energy outward as light and heat. 4 million tons per second sounds enormous, but compared to the sun's total mass, 2 times 10 to the 30th kilograms, it's negligible. Over the sun's 10 billion year lifetime, it will lose less than 0.1% of its mass. But even that tiny loss has consequences, because the sun's gravitational pull depends on its mass. As the sun loses mass, its gravity weakens. And as its gravity weakens, the planets drift slowly outward, their orbits expanding to maintain the balance between velocity and gravitational pull. Scientists have calculated that Earth's orbit is expanding by about 1.5 centimeters per year, roughly half an inch. That's incredibly slow. Over 1 million years, we'll drift outward by about 15 kilometers, or 9 miles. Over 1 billion years, perhaps 15,000 kilometers. Still, a tiny fraction of our 93 million mile distance. But it's real, measurable, and it reminds us that even the most stable orbits are not static. They breathe, they shift, they respond to forces so subtle, so gradual, that they unfold over timescales longer than human civilization has existed. The most distant threat, and perhaps the strangest, involves the motion of the sun itself. The sun is not stationary. It orbits the center of the Milky Way galaxy, completing one full orbit every 225 to 250 million years, a period astronomers call a galactic year. As the sun moves, it passes through different regions of the galaxy, some denser than others. Every 20 to 30 million years, the sun crosses the galactic plane, the densest part of the galaxy's disk, where stars' gas and dark matter are more concentrated. During these crossings, gravitational interactions increase. The tidal forces from the galaxy's mass distribution can disturb the Oort cloud, sending comets streaming into the inner solar system. Some studies suggest that Earth's mass extinction events like the one that killed the dinosaurs, correlate loosely with these galactic plane crossings, though the evidence remains controversial. There's also the possibility, remote but real, that the sun could pass near another star. Stars in our neighborhood are separated by light years, but over millions of years they move. Some drift closer, some drift away. About 70,000 years ago, a red dwarf star called Schultz's star passed within about 1 light year of the sun, close enough to potentially disturb objects in the outer Oort cloud, though no significant effects have been detected. In the distant future, the star Gliese 710, currently about 63 light-years away, is projected to pass within about 10,000 astronomical units of the sun in about 1.3 million years. That's still far outside the orbits of the planets. Neptune sits just 30 astronomical units from the sun, but close enough to disturb the Oort cloud and potentially trigger a comet shower lasting thousands of years. None of these threats will destroy Earth's orbit in the near future. The solar system is remarkably stable over timescales relevant to human civilization. Our orbit today is almost identical to what it was 1 million years ago. It will be almost identical 1 million years from now. But over billions of years, over the deep time that planets experience stability, becomes more fragile. Orbits shift. Gravitational resonances amplify small perturbations. Chaos theory takes hold tiny differences in initial conditions, growing exponentially over time until predictions become impossible. Scientists have run simulations of the solar system's future, integrating the equations of motion for all the planets over billions of years, accounting for every gravitational tug, every subtle interaction. The results show that while the inner planets, Mercury, Venus, Earth, Mars, remain stable for at least 1 billion years, in most simulations, there's a small but non-zero chance that Mercury's orbit could become unstable, its eccentricity growing until it either collides with Venus or is ejected from the solar system entirely. And if Mercury's orbit destabilizes, it could trigger a cascade. Venus might be perturbed. Earth's orbit could shift. The inner solar system, stable for billions of years, could unravel in just a few million. The probability is low. Less than 1% over the next 5 billion years. But it's not zero, and that uncertainty, that fundamental unpredictability inherent in chaotic systems, means we can never be completely certain what the solar system will look like in the deep future. What we know is this Earth's orbit is stable now. It has been stable for as long as life has existed, and barring an extraordinary event, a rogue planet, a nearby supernova, a close stellar encounter, it will remain stable for millions, perhaps billions of years to come. But stability is not permanence, and the universe, patient and indifferent, is always moving, always shifting, always evolving toward states we cannot predict. The dance continues, yes, but the music is not eternal. And eventually, billions of years from now, the sun itself will change in ways that make Earth's current orbit impossible to maintain. 5 billion years from now, the sun will die. Not suddenly, not in an explosion, but slowly, gently swelling into a red giant so vast it may swallow the inner planets whole. And Earth, if it still exists, will be nothing like the world we know. The question isn't whether our orbit will survive. The question is whether Earth itself will. The sun has been burning for 4.5 billion years. Hydrogen fusing into helium in its core, releasing energy that keeps a star shining, keeps the planets warm, keeps life alive. But that fuel is finite, and the clock is ticking. Right now, the sun is middle-aged, stable, predictable. It converts roughly 600 million tons of hydrogen into helium every second, and in the process loses about 4 million tons of mass as energy, light, and heat radiating outward into space. That lost mass, as we've touched on, weakens the sun's gravity slightly, allowing Earth's orbit to expand by about 1/2 inch per year. But the sun isn't just losing mass. It's also getting brighter, slowly, imperceptibly, but measurably. When the sun first formed, it was about 70% as bright as it is today. Over the past 4.5 billion years, as helium accumulated in the core, the sun's density increased, its core temperature rose, and fusion rates accelerated. The result? A gradual, steady increase in luminosity, about 10% brighter per billion years. This trend will continue. In about 1 billion years, roughly 1/5 of the time, Earth has already existed. The sun will be about 10% brighter than it is now. That might not sound like much, but 10% more energy reaching Earth is enough to trigger a runaway greenhouse effect. Here's how it happens. As the sun brightens, Earth warms. Oceans evaporate faster. Water vapor itself, a powerful greenhouse gas, accumulates in the atmosphere, trapping more heat. The warmer it gets, the more water evaporates. The more water in the air, the hotter it becomes. A feedback loop. Unstoppable once it begins. Scientists estimate that within 1 billion years, Earth's surface temperature will rise above the boiling point of water. The oceans will evaporate completely, escaping into space as the atmosphere is stripped away by solar radiation. The surface will become barren, dry, lifeless. A second Venus scorched and sterile under a sun too bright to allow liquid water. Life on Earth, if it still exists by then, will retreat underground into deep caves or geothermal vents clinging to the last pockets of moisture. But even those refugees will fail eventually. Within 1.5 billion years, even extremophile bacteria organisms that survive in boiling acid or frozen ice will find Earth uninhabitable. And Earth's orbit? It will continue, expanding slowly as the sun loses mass. By the time the oceans boil, Earth may sit 94 or 95 million miles from the sun instead of 93. A small shift. Not enough to save us, but the real transformation begins 5 billion years from now, when the sun exhausts the hydrogen in its core. Fusion will stop. The core will contract under its own gravity, heating up until hydrogen in a shell around the core ignites. This shell burning releases even more energy than core fusion, causing the sun's outer layers to expand dramatically. The sun will become a red giant. Its radius will swell from 700,000 kilometers, less than 1 astronomical unit, to perhaps 1.2 astronomical units, or about 112 million miles. That's large enough to engulf Mercury's orbit, large enough to swallow Venus, and depending on how much mass the sun loses during the expansion, possibly large enough to reach Earth's orbit. Will Earth be swallowed? Or will we drift outward, just enough to survive? The answer depends on two competing effects. First, the sun will lose a significant amount of mass during its red giant phase, perhaps 25 to 30% of its current mass blown away by intense stellar winds. As the sun loses mass, its gravitational pull weakens and Earth's orbit expands. Some calculations suggest Earth could drift outward to about 1.5 or even 1.7 astronomical units, far enough to stay outside the sun's expanded photosphere. But there's a second effect working against us tidal forces. As the sun expands, its outer layers will reach closer to Earth, creating drag. Not the kind of drag you feel in air or water, but tidal drag gravitational interactions between Earth and the sun's extended atmosphere that slowly sap Earth's orbital energy, causing us to spiral inward, which effect wins mass loss pushing us outward or tidal drag pulling us inward. The calculations are uncertain. The models disagree. Some simulations show Earth narrowly escaping, drifting just beyond the red giant's edge, scorched and airless, but intact. Others show Earth spiraling inward, skimming the sun's outer layers, friction heating the surface until the rocks themselves vaporize, and finally plunging into the star's core, where we are disintegrated completely. A study published in the journal Nature in 2008 by astronomers Klaus-Peter Schroeder and Robert Conan Smith ran detailed simulations accounting for both mass loss and tidal effects. Their conclusion: Earth will not survive. The tidal drag is too strong. Even as the sun loses mass and our orbit tries to expand, the drag from the sun's bloated atmosphere will pull us inward. Within about 7.6 billion years from now, roughly 2.6 billion years after the sun becomes a red giant, Earth will spiral into the sun and be destroyed. It's not certain. Other models suggest different outcomes, but the consensus leans toward destruction. Earth, the planet that has hosted life for nearly 4 billion years, will end its existence inside the star that gave it light. And what about the outer planets? Jupiter, Saturn, Uranus, Neptune. They sit far enough out to survive the red giant phase. In fact, they may benefit from it. As the sun swells and brightens its habitable zone, the region where liquid water can exist will shift outward. Moons like Europa Enceladus and Titan, currently frozen and covered in ice, will thaw. Subsurface oceans will warm. For a brief period, perhaps a few 100 million years, these moons might become oases of liquid water, warmed by a dying sun, hosting environments that could in theory support life. But the warmth won't last. After the red giant phase, the sun will shed its outer layers, creating a planetary nebula, a glowing shell of gas expanding into space. What remains of the sun will be a white dwarf, a dense hot core about the size of Earth, no longer fusing hydrogen, slowly cooling over trillions of years. White dwarfs emit light, but not much. They're remnants, embers. The habitable zone around a white dwarf is incredibly close, perhaps just 500,000 miles from the star, far closer than Mercury ever orbited. Any planet in that zone would be tidally locked one side, always facing the star, the other frozen in eternal night. Could life exist around a white dwarf? Possibly. Some astronomers speculate that planets or moons surviving the red giant phase might migrate inward, settling into the new habitable zone, their surfaces warmed by the faint glow of the dying star. But these are speculations, distant, uncertain, beautiful in their strangeness. What we know for certain is this Earth's orbit as it exists today is temporary. Not in human terms, it will remain stable for millions, even hundreds of millions of years, but on cosmic timescales, on the timescales stars measure, our current orbit is fleeting, a moment, a breath. And yet, knowing this doesn't diminish the wonder. If anything, it deepens it. The fact that we exist at all, that Earth has remained in the habitable zone for billions of years, that the conditions have been stable enough for life to arise, to evolve, to become complex, to become conscious. This is extraordinary. The window of habitability is narrow, the conditions precise, the timing from a cosmic perspective almost miraculous. Think about it. If Earth had formed just 10% closer to the sun, we would have followed Venus's path. Runaway greenhouse scorched surface, no life. If we'd formed 10% farther out, we might have frozen locked in permanent ice ages, liquid water, a rarity. But we formed here, at this distance, with this velocity, and for 4.5 billion years, through asteroid bombardments, volcanic eruptions, ice ages, and warm periods, mass extinctions, and evolutionary explosions, Earth's orbit has held steady. That steadiness allowed life to persist, to adapt, to thrive, and eventually to look up at the stars and ask, why are we here? How does this work? What keeps us falling without ever landing? Now we know. Velocity and gravity, ellipses and eccentricity. space-time curvature, the slow loss of the sun's mass, the delicate balance maintained not by design, but by the mathematics of motion inherited from the swirling disk of gas and dust that collapsed to form the solar system billions of years ago. And we know something else: this balance will not last forever. The sun will change. Earth's orbit will shift. And in the deep future, the world we call home will either drift into the cold or spiral into the fire. But here's the strange, comforting truth. By the time any of that happens, humanity, if it still exists, will be long gone from Earth. Not destroyed, but transformed, spread across the solar system, perhaps beyond. We may terraform Mars, mine the asteroid belt to build habitats in orbit around Jupiter's moons. We may leave the solar system entirely traveling to other stars, finding new worlds, new orbits, new skies. Or we may not. We may fail. We may vanish. Another brief chapter in the long history of life on Earth, leaving only fossils behind, traces in the rock for some future intelligence to discover and wonder about. Either way, Earth's orbit will continue without us. The planet doesn't need us. It never did. It will keep falling around the sun, faithful to the laws of motion, until the sun itself transforms and the rules change, and the ancient dance 4.5 billion years old finally ends. But until then, we have time. Not infinite time, but enough to understand, enough to appreciate, enough to look up at the night sky and truly know that we are not standing still. We are moving. We are falling. We are part of a cosmic ballet so old, so vast, so precisely choreographed by gravity and geometry, that even knowing the ending doesn't diminish the beauty of the performance. And as we drift toward that distant conclusion, there's one more perspective to hold a wider view that places Earth's orbit not just within the solar system, but within the galaxy, within the universe itself, where every orbit is nested inside another, every motion part of a larger motion, every fall part of a deeper fall that has no beginning and no end, only continuation, only the endless, gentle unfolding of space and time. Right now, as you rest in this quiet moment, Earth is moving at 18.5 miles per second around the sun. We've traced that journey together through these past hours, the velocity, the balance, the mathematics, the history of understanding. But there's something we haven't said yet, something that changes everything once you see it. Earth isn't just orbiting the sun. The sun is orbiting too. The sun, along with Earth and all the planets, all the asteroids and comets, the entire solar system, we're all falling together around the center of the Milky Way galaxy, right now, at a speed that makes Earth's orbital velocity look like a gentle stroll. 514,000 miles per hour. That's how fast the sun moves through the galaxy. Roughly 143 miles every single second. Fast enough to cross the entire United States coast to coast in less than half a minute. And at that speed, moving through space thick with stars and dust and dark matter, it takes the sun approximately 225 to 250 million years to complete one full orbit around the galactic center. Astronomers call this period a galactic year. And Earth, along with everything in the solar system, has completed roughly 20 galactic years since it formed 4.5 billion years ago. Think about that. 20 laps around the galaxy. 20 times the sun has traced its immense circle through the Milky Way's spiral arms, carrying Earth with it like a passenger on a cosmic carousel. When dinosaurs walked the Earth 230 million years ago, the sun was on the opposite side of the galaxy from where it is now. When the first multicellular life appeared 600 million years ago, we were less than 3 galactic years old. And we're not just moving in a circle. The sun bobs up and down as it orbits, oscillating above and below the galactic plane like a horse on a carousel. It takes about 64 million years to complete one full oscillation, rising above the plane, then sinking below, then rising again. Right now, we're about 60 light years above the midplane, climbing upward, and will reach our maximum height of about 230 light years above the plane in about 14 million years before descending again. This bobbing motion has consequences. Every time the solar system crosses the galactic plane, the densest part of the galaxy's disk gravitational interactions increase. The Oort cloud gets disturbed. Comets rain inward. Some researchers have suggested that mass extinction events on Earth correlate loosely with these crossings, though the data remains controversial and incomplete. But here's what's certain. Earth is not moving through empty space. We're moving through a galaxy, and the galaxy itself is moving through the universe. The Milky Way isn't stationary. It's falling toward the Andromeda Galaxy, our nearest large galactic neighbor, at about 70 miles per second. In approximately 4 billion years, roughly the same time, the sun begins its transformation into a red giant. The Milky Way and Andromeda will collide. Not a violent collision. Galaxies are mostly empty space. Stars rarely collide directly, but the two galaxies will pass through each other, the gravitational fields interacting, pulling stars and gas into new configurations. Over hundreds of millions of years, they'll merge, forming a single elliptical galaxy that astronomers have already nicknamed Milkomeda. What will happen to Earth during this collision? Probably nothing dramatic. The distances between stars are so vast that even as billions of stars intermingle, the odds of our sun being significantly perturbed are quite low. We might end up in a different part of the merged galaxy. Our view of the night sky will change completely, filled with new constellations, new clusters, the combined light of 2 galaxies worth of stars. But our orbit around the sun, likely undisturbed, and beyond the local group of galaxies beyond Andromeda and the Milky Way and the dozens of smaller galaxies gravitationally bound to us, there's an even larger motion. The entire local group is falling toward something called the Virgo supercluster, a vast collection of thousands of galaxies about 55 million light-years away. And the Virgo supercluster itself is falling toward an even larger structure, the Laniakea supercluster, which contains more than 100,000 galaxies spread across 520 million light-years. And all of it, Laniakea, Virgo, the local group, the Milky Way, the Sun. Earth, you all of it, is moving together, pulled by gravity on scales so immense they defy comprehension. We are falling through the universe in nested orbits, circles, within circles, each motion carrying us forward, each fall perfectly aimed at nothing, each path traced by gravity's patient hand. This is the cosmic perspective, the realization that there's no stillness anywhere, no fixed point, no center. Everything moves. Everything falls. From planets to stars to galaxies to superclusters, the universe is in constant motion. Every object following geodesics through curved space-time. Every orbit, part of a larger orbit. Every dance part of a grander choreography that began with the Big Bang 13.8 billion years ago and continues still. And here's what makes it beautiful. Despite all this motion, despite falling at hundreds of miles per second through a galaxy, falling at hundreds of miles per second through a universe expanding in all directions, at once we feel none of it. The coffee in your cup sits still. The air around you doesn't rush past. The ground beneath you feels solid, motionless, eternal. Because motion is relative. And when everything around you moves together, the air, the ground, the planet, the solar system, the galaxy, there's no reference frame to betray the speed. You are part of the motion, inseparable from it. And so, it feels like rest. This is what Galileo understood 400 years ago when he defended Copernicus. This is what Newton proved with mathematics. This is what Einstein revealed with geometry. That motion and stillness are two perspectives on the same reality, and which one you experience depends entirely on where you stand and what you measure against. From Earth's surface, we are still. From the sun's perspective, we're racing at 18 miles per second. From the galactic center, we're screaming through space at 500,000 miles per hour. And from the perspective of a distant galaxy, billions of light years away, we're part of a universe expanding so rapidly that space itself is stretching, carrying galaxies apart faster than light can travel between them. All of these perspectives are true, all of them real, all of them valid. The universe doesn't choose one over the other. It contains them all simultaneously nested together like Russian dolls, each layer revealing a deeper motion, a larger fall, a grander orbit. And what does this mean for the question we started with? What really keeps Earth in orbit around the sun? The answer now feels both simpler and more profound than when we began. Earth orbits the sun because we're moving through curved space-time at exactly the right speed to trace a geodesic, a path that feels straight to us, but appears curved from outside. We orbit because 4.5 billion years ago, when the solar system formed from a collapsing cloud of gas and dust, we inherited a specific velocity and a specific distance, and those two numbers locked together by gravity's mathematics have kept us falling ever since. But more than that, we orbit because everything orbits, because falling is the natural state of matter in a universe governed by gravity, because there is no stillness, only motion, and because the motion we call orbit is simply falling aimed so precisely that the destination keeps moving away, creating a loop that can, in principle, last forever. This is the universe we live in, not a clockwork mechanism ticking predictably through predefined paths, but a dynamic, living cosmos where every object responds to every other, where tiny perturbations compound over eons, where stability emerges not from rigidity, but from balance, not from permanence, but from patterns that persist long enough to seem eternal. Earth has orbited the sun for 4.5 billion years. It may orbit for billions more. But eventually, the sun will change, and our orbit will end, either in fire or ice swallowed, or abandoned, transformed into something we can't predict from where we stand now. But that ending, distant as it is, doesn't diminish the beauty of the orbit we're tracing right now. If anything, knowing that it's temporary makes it more precious, more worthy of wonder, more deserving of the attention we've given it tonight. Because this is what science offers us, not just answers, but perspective, not just knowledge, but connection, the realization that we are not separate from the cosmos, not observers standing outside, but participants within it, made of the same atoms, following the same laws, tracing the same curves through space-time that stars and galaxies trace. You are orbiting the sun. The sun is orbiting the galaxy. The galaxy is falling through the universe, and all of it, from the smallest motion to the largest, is held together by gravity, the weakest force in nature, yet the one that shapes everything on cosmic scales, the one that built galaxies from clouds of hydrogen, the one that gathered planets from dust, the one that keeps Earth fallen around the sun without ever landing. And maybe, just maybe, when you wake up in the morning and the sun rises once again, you'll feel it differently. Not as a static scene, but as evidence of motion, as proof that you've completed another lap, another day, another quiet revolution through space carried forward by momentum, older than mountains, guided by forces too vast to see, but precise enough to predict your position 1,000 years from now, within seconds. We've traveled far together through this exploration, from the stillness that masks motion to Newton's garden to Einstein's geometry, from ellipses to red giants to galactic orbits, from the question of what keeps us in orbit to the deeper question of what it means to fall through a universe that has no ground, no center, no final resting place. And the answer, perhaps, is this: we are kept in orbit not by any single force or mechanism, but by the fundamental nature of existence itself, by the curvature of space-time, by the conservation of angular momentum, by the ancient velocity inherited from the solar system's birth, by the mathematics of gravity playing out across billions of years, by the fact that in a universe governed by physics rather than purpose, the stable orbits are the ones that survive, and we are here because our orbit was stable enough to last. It's not design. It's not miracle. It's simply physics. And yet, physics, when you really look at it, when you trace its implications from falling apples to orbiting planets to spiraling galaxies, is more beautiful than any story we could invent. Thank you if they're undone. For letting curiosity lead you, for following the mathematics and the metaphors to their quiet conclusions. The universe is vast. The questions are endless. And there are more stories waiting in the darkness between stars, more wonders hidden in the equations, more journeys to take through the gentle mystery of existence. Until we meet again under distant skies, rest well. Dream of orbits and ellipses of curves traced through the dark, and know that even as you sleep, you're moving, falling gracefully, endlessly, perfectly, through a universe that knows exactly how to hold you. Sleep well. Dream gently. Good night.